Hello everyone, welcome to our channel Only Physics JEE Grad. So today we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter Dual Nature. This will be the second video on it, but in the first video there were we have discussed about 24-25 questions, right, on the topic photoelectric effect, right? So there were some questions left. So we'll go through them first and then we'll move on to the second topic, which will be on the de Broglie and Davison-Germer experiment. Okay. So let me check. So we have done 21, 22, 23. It's 23 and this was 24. Yes. So we have discussed 24 questions. So we are left with 5 questions. So let's first discuss those 5 questions. Okay. So, okay. So here are the 3 questions, right? Let me zoom in a bit so that it will be easily visible. Okay, right. So we have our 25th question. Okay. So what is this in this question? The maximum kinetic energy of photoelectrons emitted from the surface when photon of 6 electron volt fall on it is 4 electron volt. Okay. So the maximum kinetic energy is how much? It is 4 electron volt, right? So stopping potential we have to find. So kinetic energy is equals to E into V, right? So we'll get V as that this is potential difference, right? So this V is actually potential difference. So potential difference will be equal to 4 volts. Okay, you can also write it as delta V. So it will be okay. So quite easy question. Now let's move on to the 26th question. Okay, so let's leave this question for a second. Let's do this question. Okay, so let me do this question first. So here, this is a simple graph question, right? So we know the formula. It is V naught equals to E V naught equals to H C by lambda minus phi, right? So this is a photoelectric equation. So what will you write here is V naught will be equal to H C by E. This is 1 upon lambda minus phi. Okay. So if we want to make a graph of V naught versus lambda, so V naught will be Y. This will be some M. This will be 1 upon X. Okay. So I'm making the graph and this is some again constant. So this is some constant again. Okay. So let's not write this as m because with the m you will think it's a slope, right? So we don't know if it is a slope for this graph or not. I just write it k. Okay. So this is these type of graph. So as you can see, it will continuously decrease and it's like a hyperbolic graph, right? So which option is correct? So V naught versus lambda, right? We have put x as lambda, so A is correct. Okay. Now for V naught versus 1 by lambda. So in the second graph, we have to put V naught as y. So here V naught was equals to y, okay, and x was lambda. Now here V naught we have to put as y, and 1 by lambda is equals to x. So we'll get V naught is equals to, this is again k. So this is y, right? So y k x minus c. So this is a straight line, right? For this graph, it's a straight line. So which one is this? It is this, right? So A and C are correct. Okay, so let's move on to our 27th question. Now, this 27th question, this 27th question is a very interesting question, okay? And there is another question which is slightly more complicated than this one, okay? So let's do this first and then we will do that complicated one, okay? Now, Okay, perfect. So in this question we have, let me decrease this length a little bit, right? So we have a filament of light bulb has a surface area 64 millimeters square. Okay, so we have a bulb whose area is this. The filament can be considered as a black body at a temperature this. So temperature we have is 2500 K. Okay. Now emits radiation from a point source viewed from a very far. So we have this as a point source. Now this filament of the bulb, its surface area is 64 millimeter square. Okay, right? Now uh, and this filament can be considered as a black body emitting radiation like a point source. So it is considered like a point source. Okay, at night the light bulb is observed from a distance 100 meter. So from here, let's go. This is a P point. Okay, where observer is here. Okay, so this is a source, and this distance is 100 meter. Now assume that the pupil of the eyes of the observer to be circular with a radius 3 millimeter. So we have eye like this. So let me make the eye like this. Okay, so this is our eye. So this is our eye, right? Of course, the observer will be at this place, of course, right? If eye is here, then observer is here, right? And this the radius of this eye is 3 millimeter, right? Okay. Now we have given Stefan's Boltzmann constant, which is sigma, right? So sigma is given, which is 5.67 into 10 raised to power minus 8. Okay. And this is Wien's constant. So B is given 2.9 into 10 raised to power minus 3. Perfect. So in this question, let's find. Okay, Planck's constant is also given and speed of light is also given. Now, in the first part, so we have to check these options, which one are correct. So power radiated by the filament is in the range 642 watt to 645 watt. Okay, so let's find this first. So like if this is a black body, if this is a black body, then energy it will emit will be equals to sigma, right? Sigma A T to the power 4. Okay, and there will be E also, so E will take it as a 1, right? So for black body E is 1. Okay, so as it is a black body, so E will be 1. So if you find, uh we'll get power from it, right? Yes, so we'll get power from it. So power will be equal to sigma A E T to the power 4. So let's put those values. So you'll get 5.67 into 10 raised to power minus 8. And the area, so area we have to take of this source, so it will be 64 into 10 raised to power minus 6 meter square, right? And then unit will get cancelled, so E is 1 into, and temperature is 2500 to the whole power 4. Okay, so if you calculate this, we will approximately get 142 watts, which is not correct. Okay, so in this question, it is asking, it has given the power should be in between 642 to 645, which is incorrect. So A option is incorrect. Now let's move on to other. The radiative power entering into the eye of an observer is in the range of this. Let's check. Now, the first thing to solve these type of question is we have to consider the source and the area around which it is illuminating it, right? So we have to make a sphere like this. We have to make a sphere like this, right? So in this, so this is a sphere, okay? So this is a sphere. So this source is illuminating this surface area, okay? This surface area it is illuminating. Now, if I want to find the intensity, so intensity will be what? It will be power upon this total surface area. So it will be power upon the total surface area of the sphere. It will be 4 pi 100 square. It will be 4 pi 100 square, right? So if you put those values, you will get something. Now we get the intensity. Now we have to find how much our eye is receiving the power. Okay. So actual in reality we need this area. In reality we need this area, but it will be approximately equal to this. Why? Let me derive it. So let's find this area. So we have to use the concept of solid angle, right? So let's make this, and let's say this is theta, this is capital R, and this is small r, right? This is small r. So solid angle will be 2 pi 1 minus cos theta. And if we get the solid angle, then this area, let's say this area is A. Okay, so let's say this area is A. Now, if you want to find this area, it will be r square into the solid angle, right? So let's find this. So r square solid angle will be 2 pi into 1 minus cos theta. And now cos theta we don't know, right? So this we don't know, base we don't know, but we know perpendicular. So for cos theta we can write it as 1 minus sine square theta, right? So this area we are going to find. So area will be 2 pi r square. This will be 1 minus root 1 minus sine square theta. So it will be r square by capital R square. So small r square by capital R square. Now we are going to use a binomial approximation here. So how will it work? So if r by r is much less than 1, is it? This r is 3 millimeter and this capital R is 100 meter. So yes, this is true. So we can use this binomial expression and we get area as 2 pi capital R square. This will be 1 minus r square by capital R square into 1 by 2, right? Okay. So if you solve, we'll get 2 pi r square and 1 minus 1, this will be plus, so it will be 1 by 2 small r square by capital R square. And now 2 and capital R square will get cancelled and the area we'll get is actually pi small r square. And this area is actually this area, right? So this area and this area is actually almost equal, right? So that's why we take this area. Okay, now the intensity we get, this was our intensity, right? If this was our intensity, then the power received by our eye will be into pi small r square, right? So I'll be putting it here. So the power received by eye, the power received by eye will be this power p upon 4 pi 100 square into pi small r square, and this small r is we have, so it will be pi 3 millimeter square. Okay, so let's put all those values here. So we will get 142 divided by 4. This pi will get cancelled, right? So it will be 10 raised to power 4 into 3 will be 9 into 10 raised to power minus 6. Okay, so you will get, if I use the calculator really fast, so 142, so it will be approximately 3.2 into 10 raised to power minus 8. Okay, so this is the power received by our eye. So power received, again I'm writing it by eye. Okay, so this will be the answer for B option. So it is saying the radiated power entering into the observer eyes between this. So this is correct. Yes, so this is correct. Let's move on to option C. Let's move on to option C. So it is saying if the wavelength corresponding to the maximum intensity is 1160. So we have to find the wavelength. So this is quite easy. We know the lambda max into T will be equals to Wein's constant, right? So lambda max will turn out to be, this is 2.9 into 10 raised to 1 minus 3 divided by divided by this temperature. So temperature is 2500, right? So you will get 1190 nanometer. You'll get 1190 nanometer. So I think this option is also correct. Okay. Yes, C is also correct. 1190 or 1160. 1160 you will get. Okay. Now, what is other D option? That taking the average wavelength of emitted radiation to be 740. So you have to take the wavelength as 740. The total number of photon entering per second into once per second into one eye of an observer is in the range this. Okay, so power we get this, right? So if the power is this, so it will be n upon t, right? So n upon t is number of photon received per second into the energy of one wave, right? Energy of one photon. So it will be hc by lambda, right? Now lambda we have to take as 1740. So this n by t will be equals to 3.2 into 10 raised to power minus 8, and for hc we can write it as 1240. So it is divided by 1240 and it is multiplied by lambda. So lambda will be 1740 we have to take, right? So 1740 we have to take. So if you calculate, if I calculate it really fast, uh, so we will get 3.2 into 1740 divided by 1240. So you will get, mm, that is correct, right? So it should be equals to 3.2 into 1740, okay, divided by 1240. So I get 4.49 into 10 raised to power minus 8. Hmm? Is this correct? Is wavelength is in nanometer or angstrom? So the wavelength is taken as 1740, right? So Hc was 1240, it will be in the denominator, and 1740 will be in the numerator. Uh, if I use the equation 3.2 into 10 raised to power minus 8 into lambda is 1740 into 10 raised to power minus 9, right? Let's use this. H is 6.63 into 10 raised to power minus 34 into C. C will be 3 into 10 raised to power 8. Okay. Now from this you'll get answer, right? Let's see. 3.2 into 1740 divided by 6.63 and then divide by 3. What? So we are getting 2.799 into 10 raised to power 11. Hmm? Am I doing some mistake or what? Oh, okay, okay. So yes, it was in electron volt, right? And we are using volt. So this is wrong, right? So this is wrong. So yeah, this is correct, right? Because this is in watt and this Hc was in this 12.1240 is in electron volt nanometer, right? So we can't use here. So yeah, this is correct. So we get n by t will be this. Okay, so C option is this 2.8 something. So yeah, so D option is also correct. Okay, so the main concept here was this, the concept of this area. Okay, so the power received, you should remember it. It will be power, the total power emitted by the source divided by the area of the sphere. So it will be 4 pi r square into, you multiply it whatever the area you want to look for. So we are looking the power received by the eye, so you just multiply it by pi r square. You should not write it as like 4 pi r square. Okay, it will be pi r square because the approximation we are doing. Okay, now another similar question like this, but it is a bit more complicated, will be like, will be will be discussing here. Okay, so let me pose this question really fast. So it must be this, I think. Right. So this is the another complicated question. Okay. So let's just first discuss this one. Let's first discuss this 28th question. Then we'll move on to this question. When a beam of photon of intensity this, so the energy of photon is 10.6 eV and intensity is given 2 watt per meter square, right? 2.4. Okay. Uh, and on the platinum surface. Okay, so we have a surface like this, right? And the area of this surface is 1 into 10 is to the power minus 4 meter square. And the work function is also given. It is 5.6 eV. Now it is given 0.53% of incident photons eject photoelectrons. Okay, so whatever be the number of photons, only 0.53% from 0.53% will get the electrons. Okay, that's quite low, right? Now find the number of photoelectrons emitted per second and their minimum and maximum energies we need to find, right? So let's first find the number of photons which are uh, coming on this surface, right? So we have the photon energy is this and the intensity is this, right? So the number of photons per second will be intensity divided by energy of each photon into the area, into the area, right? Okay, so intensity is 2 into area is 10 is to power minus 4 divided by photon, energy of photon is 10.6 into where it is EV, so it is in EV, so it will be 1.6 into 10 is to power minus 19. So this is n by t, right? And this is actually number of photons per second on our surface, right? So let's calculate this really fast. I'm going to use the calculator again. So 2 divided by 10.6 divided by 1.6, so we will get 0.1179 and let's make it 2. Okay, so it will be 0.12. Let's make it 0.12 into 10 is to power plus 15, right? So it will be 1.2 into 10 raised to power 40. Okay, so this is the number of photons which are uh, yes, which are incident, which are uh, illuminating our surface, right? Okay, so from that 0.53% of the photoelectrons are only 0.53, right? So let's find the number of electrons emitting per second from the surface. It will be 0.53% of this. So 0.53 divided by 100 into 1.2 10 raised to power 40. Right? Okay. So how much it will be? So it will be we are doing correct, right? Okay, we'll see. So it will be 0.53. I'll use the calculator again into 1.2, right? So it will come out to be 0.63 into 10 raised to power 12. So it will be 6.3 into 10 raised to power 11 electrons per second. Okay, so these are the electrons which will be emitting from the surface, right? Now, if we want to find the minimum and the maximum energies, so minimum will be zero, right? So minimum energy, minimum kinetic energy of electron will be zero, and the maximum will be 10.6 was the initial energy of photon minus the work function. The work function was 5.6, so we will get 5.1. Oh, so 5.0 electron volt, right? So we'll get 5.0 electron volt. This will be the maximum energy. Okay, so this was quite easy. Now let's move on to the question which causes the headache. Okay, now this is the actual question which this was the 29th. Okay, so this is the same question like we have just done, like the two question before, but it is slight more complicated. Okay, and the concept is again the same. The power received by the observer will be P upon the area of sphere into pi small r square, right? So the concept is similar. Okay, let's start. So I won't be doing the calculation here. I'll just put the answer. Okay. Now we have given a monochromatic source radiating 6,000. So lambda is 6,000 angstrom, right? And the power of the source is 2 watt. Now an aperture A of diameter. So this has a diameter 0.1. So let me start making a diagram. So let's say we have a source like this. So this is our source. Okay. Now we have aperture. So it looks like this. So I will just make a circle like this. Okay. So let me make it over here. Okay. Now, are you getting me? Let me make the perfect diagram for this. For this source, this aperture is like this, right? So the source will be illuminating this surface area. Okay. Are you getting me? And the radius of this, so I will put it at small r. So it will be 0.1 divided by 2 meters, right? And this distance is again 0.6. So let me put it as capital, right? Okay, on larger screen, this is a screen. Okay, so we have a screen here. So we have a screen. Let me make it in with the blue. So we have a screen. I will rotate it. So let me rotate this. So we have a screen over here. So it's quite far away. Let's just put it here. And the distance is this. So the distance is actually 6 meter. So quite low, quite away from the source. And there is a detector also, surface area is this. So there is a small detector. So here there is a small detector. Its area is actually 0.5 centimeter square. Okay. So to read, so we should read this question very carefully. Okay. The efficiency of the detector. for the photoelectron generation per second is 0.9, right? So whatever be the photons are like illuminating this area, the number of electrons which it can detect will be 0.9. So this is quite important. Okay, so be careful. Now let's move on to our questions. So first, in the first A part, we have to find the calculate of photon flux at the center of the screen and photoelectron in the detector, or photocurrent in the detector, right? So it will be according to number of electrons, right? So if the number of electrons we can get, we'll multiply it with the charge and then we'll get the answer. Okay, so it's a long way. Let's first find the photon flux at the center of the screen. Okay, here. Now, look, the power of this source is 2 watt and it is illuminating this 4 pi r square area, and this, the we will say like this is our first observer. Let's say it's observer 1, and let's say this is our observer 2. Okay, so what will happen, this source will like uh, illuminate this whole surface area, but the only this part of the energy will it will receive, right? So I will use the formula directly. So power, I will write it as power received by O1 will be equals to the total power, it is 2, divided by 4 pi r square. So it will be 4 pi 0.6 square into the area of this. So it will be pi 0.1 by 2 to the whole square. Now you will say why I use this, because this small r square by capital R square is much less than 1. That is why I use this. Otherwise, I have to use the concept of solid angle to find the exact, right? Okay. So let's say this will receive, so power received by this will be this. Okay. Right. So it will receive power. How much? So let's say the O1 will receive power P1 and the number of photon it will receive is N1, right? So this is P1. So P1 will be this, right? So if I cancel it out, let me cancel it out. So how much you will get? So look, pi will get cancelled. This will be 2. So this will be 0.1 into 0.1 divided by 4, and this will be 4 into 0.6 into 0.6. So if I use the calculator really fast, we'll get 1 divided by 16 and divided by this 36, right? So we will get 1.7 into 1 2 3, so it will be 10 raised to power minus 3 watts. Okay, so if I want to find n1, let's find this n1. So n1 will be, the power is this, right? So the power is this divided by, right? So how much it will be? Okay, so let me check if there is, so this will be 4 and okay, so this will be 2, right? So this will be 2. Now, so it will be 3.47, right? So 3.47. So I'll write it as 3.5. Okay. So I'll rub it, and so yes, so it will be 3.5. Yes. So power at here, so power at this observer will be this. So if I want to find the number of photons which will be here, right, at the observer 1, number of photons like received by the observer per second. So it will be P1 divided by energy of photons, right? So let's first find energy of photon. So energy of photon will be hc by lambda, right? So hc will write 12400 divided by 6000. So it will be in electron volts, right? So if you calculate this, we'll get 12400 divided by 6000 So we will get approximately, so it will be, um, and then we'll multiply it. So 1400 upon 6000, we have to find it in the joule. So it will be 1.6 into 10 is per minus 19. So we will get 3.3 into 10 is to power minus 19 joules. Okay. So we'll get 3.3 into 10 is to power minus 19 joule, and then we'll divide this. So we will get 3.5 into 10 is to power minus 3 divided by 3.3 into 10 is to power minus 19. So how much it will get? We'll get 1.052 into 10 raised to power 16 second inverse. So these are the number of electrons per second received by this observer. Okay, this observer. Now, now the photons, now the photons will go on this surface area, right? And they will go from here, right? Because these will move like this, so they will not be able to reach here, right? Are you getting? This aperture is used so that only the photons from here, only the photons from here will reach this, so they will move like this. So only the photons from here will move on this surface. So this observer will act like a secondary source. So it will act like a secondary source. Okay, so it will act like a secondary source. Now we have to calculate the photon flux at the center of the screen. So at the center of the screen we have to find. Okay, so again, if this is an observer, so I have to make another circle, another sphere. So we have to make another sphere considering this as a center, right? So it should look like this. It should look like this. This will be the center of that. Okay, this will be the center of that. Now this distance is how much? It will be 5.3, right? So it will be 5.6 minus 0.6, so it will be 5.4 meters. Okay, so this distance will be 5.4 meters. Now we want to find how many photons, right? So photon flux. So we have to find the number of photons in the unit area reaches here. Okay, so let's first find the number of photons, the intensity from this surface. Okay, so how will we find it? So look, this is our secondary source, so it will act like a secondary source. So this is our secondary source. Okay, this will be our secondary source. Now how will we do it? Hmm? So if we want to find the number of photons emitted per second per unit area, so it will be how much? It will be n1 divided by the area of big sphere, right? So it will be area of the big sphere, right? So it will be 1.052 into 10 raised to power 16 divided by 4 pi into how much? So it will be 5.4 square, right? So how much it will be? So if we calculate this, we should get, it will be 2.87 into 10 raised to power 13 second inverse meter minus 2. Okay, this will be the number of photons emitted per second per unit area. Okay, so, and this is actually our photon flux, because the unit area we have the number of photons received per unit area on the screen. So this will be our photon flux at where? Center of screen, right? At the center of the screen. So let me zoom. Okay, so this will be our photon flux. Okay, now, so we get our photon flux. Now we have to find our photo current. Now photo current, look on this area, if we get how many number of photons are like received by this detector, okay, and the number of electron, we can find it by multiplying by 0.9, right? So now I will write here. So let me zoom in, let me move like this. Okay, now what I want to find is, what I want to find is number of photons received by detector per second. So it will be this photon flux, right? So it will be this photon flux and multiply by pi r square, right? Multiply by pi r square. So the area is given, right? So area is given. It is 0.5, right? So let me just write it as area of detector, right? So it will be 2.87 into 10 raised to power 13 multiplied by 0.5 into 10 raised to power 4. So if we calculate this, we should get 1.435 into 10 raised to power 9 second inverse. So these are the number of photons received by the detector. Okay, but detector will receive, so these are the number of photons received by area of detector, to be precise, right? Now due to these photons, the electron will be ejecting are, so photoelectrons will be how much? 0.9 times of this. So it will be 1.435 into 10 raised to power minus 10 raised to power 9 into 0.9. So these are the number of electrons. Okay, so these are the number of electrons. Now if I want number, so photoelectrons per second is this. Okay, and we need to find the current. So we know current is Q upon T, and Q is N upon T into E. So this is actually N upon T. This is actually N upon T, and we have to multiply it by 1.6 into 10 to the power minus 19. So we'll multiply it into 10 to the power 9 into 0.9 into 1.6 into 10 to the power minus 90. So this will be in ampere. Okay, and you will get 2.07 into 10 raised to power minus 10 ampere. So this will be the photocurrent. This will be the photocurrent the detector will get. Okay, so we have to use the concept of power upon area of sphere into the area of circle two times. First here, then we have to use it here. Okay, right? So look, first this was source, then we find the power received by this observer. So it was power will be the net power divided by 4 pi r square into the pi r square of this area, pi r square of this area, right? Then we find if we get the power, then we can find the number of photons per second coming on the surface. So it will be P1 upon the energy of each photon. So it will be like this, right? Then, then, then what happens? We find the photon flux at the center of screen. How? So again, this becomes the secondary source. So it will be illuminating this whole area, right? It will be 4 pi r square and r will be 5.4. So we just write n1 divided by 4 pi r square, and this will be our photon flux received at the center of the screen. Then we have to find how much will be the current is detecting by the detector, right? So how much the current is detected by the detector. So we have to find the number of photons reached on this surface area. So again, we have to multiply photon flux with the area of detector. It will be given as 0.5 into 10 to the power minus 4, right? This we get number of photons, but number of electrons will be only 0.9 times. So we multiply this by 0.9, and for the current, we have to multiply it by E, because each electron will have 1.6 into 10 to the power minus 19 charge. So this the current we'll get. Okay. Yeah. So this question is quite uh, complicated. It's not like tough, but it is quite complicated. Okay. That makes it a hard question. Okay. Now let's move on to B part. So this was the A part, to be precise. Okay. Now let's move on to our B part. So let me copy this diagram, and we will put this diagram here again, right? So let me put this diagram here. Now the B part we have to solve. Okay. So if a concave lens L of focal length 0.6 is inserted in the aperture, right? So find the new values of photo flux, photon current, and assume average transmission of 80% from the lens. Okay, perfect. So look, what will happen if I put a concave lens here and the source is here, right? So the photons which were falling on this aperture will remain same. So it will be same. It was our N1, right? So how much our N1 was? How much our N1 was? So it was 1.052, right? So it was 1.052 into 10 raised to power 16. So N1 will remain same, right? Okay, N1 will remain same. Now, if this is the source, as soon as these photons pass through this, right? So they will diverge and will look like this. This was our source, right? So if this was 0.6, let's calculate this distance. Okay, so we will use 1 by v minus 1 by u is equals to 1 by f. So 1 by v we have to find minus this is minus 0.6 is equals to, and the focus is given is 0.6. So we will get 1 by v will be, so it will be negative, right? So this will be minus, this is plus, so it will be minus 0.6. So we will be minus 0.3, right? So this distance will be 0.3 and this will be 0.3 also. Okay, so both will be 0.3. Now the number of electrons which are falling on this aperture A will be same. Okay, and now question is saying that find the new values of photo flux, photocurrent, assume a uniform average transmission of 80% from the lens. So if the N1 was same, but the only the 80% are passing through. Okay, only 80% are passing through. So let's find the N1 dash. So it will be 80 by 100 of this N1, right? So it will be 80 upon 100 into 1.052 into 10 raised to power 16. Only this will be our new N1. Okay, from this. Now, right? So now what will happen? We have to find the photon flux. Okay, so look, after the photons pass through this, now the source become this. So this is the our actual source. So if I want to make a circle, so if I want to make a sphere, of course, so our source is this. Our source is our secondary source is this. So initially our secondary source was this. So initially this was our secondary source, right? So initially this was our secondary source, but now this will become our secondary source. So now this will be our secondary source. And if this is our secondary source, so the sphere we have to make should consider this as a center, and it should be like this, right? So this is our center, and the distance, this is 0.3 and this was 5.4. So the whole distance, this distance will be 5.7 meter, right? And our screen, and this will be our screen, right? This will be our screen, and this was our detector. So this was our detector, and this will be our screen. Okay, so now this sphere of radius 5.7 we have to consider. Okay, so flux will be, so photon flux, so photo flux will be n1 dash divided by 4 pi 5.7 square. So if you calculate this, you will get 2.06 into 10 raised to power 13 second inverse meter minus 2. So this will be our new photon flux. Okay, and if I want to calculate the new current, so new photo current, so it will be same. So it will, how will we calculate it? So it will be 2.06 into 10 raised to power 13, and the area was 2.5 into 10 raised to power minus 4 into 0.9 times of this because of the efficiency times 1.6 into 10 raised to power minus 9. So from this, if you calculate, we will get 1.483 into 10 raised to power minus 10 ampere. Okay, so this will be our new photocurrent. Okay, because initially the source was our aperture. So initial source was this. So this was our initial source. Okay, for the part A, initial secondary source. But now the source become this. So this will become the source. It is not this, right? So from there we have to make a sphere, and then it will be of the radius 5.7, and then we have to divide it by the area of the sphere, which will be 4 pi r square. Okay. So C part. So that's a headache. Okay. So the work function of emissive electron is 1. So phi is 1 electron volt. Calculate the values of stopping potential in the two cases. So we can calculate this, right? Look, these apertures, right, only limit the intensity. So stopping potential will remain same. It will not get affected, right? So we can find the stopping potential as, sorry, so it will be EV will be equals to HC by lambda minus 1. So HC by lambda, it will be 12400 divided by 6000 minus 1. So if I calculate this, 12400 divided by 6000, so it will be 2.07 minus 1, so it will be 1.07. Okay, so this will be our V naught, right? So it will come out to be in electron volt. EEV, EE will get cancelled, EE will get cancelled, so V naught will be 1.07. Okay, in both cases, because these cases will affect only the intensity, right? And intensity does not affect the maximum kinetic energy of the electron or stopping potential, right? So it will be same. Wavelength will be same, right? So it will always be 6000. Right? So this question is actually the hardest question. Okay, so it's quite tough question, right? Due to the complexity in this question is quite large, right? Okay, so let's move on to our the second topic, which is de Broglie and Aviation Jammer experiments, right? So let me put the questions in front of you really fast. So these will be the questions. So right. So there will be 13 questions which we'll be discussing. Okay. Let's start with our first question. So a beam of electron is used in Young's double slit experiment. The slit is D. The velocity of electron is decreased. So look, according to de Broglie, the wavelength will be h upon mv. If the velocity is decreased, okay, velocity is increased, then wavelength will decrease. Okay, so if wavelength will decrease, we know so the fringe width beta will be equals to lambda d by small t. So if lambda decreases, fringe width decreases. Okay, so C will be the option. Now it says no interference is observed. Look, uh, we have seen that electrons behaves like a wave. Okay, so if we take the slit width to be sufficiently less, right, sufficiently small, then interference will observe. Okay, so A will not be the option. Let's move on to our second question. So a proton has this energy E, which is equals to that of photon. So energy of photon is equals to energy of proton. Let's just say P. It's 100 keV. Okay. The wavelength of photon is lambda 2. So we know lambda 2. So lambda 2 will be hc by E. Okay. EPH. And they are both equal. So no worries. And the lambda of proton. So lambda of proton will be h upon mv, right? Or we can say it as p, momentum, right? And we can consider it a momentum. The formula of momentum in terms of energy is 2me, right? And these both are equal, so we'll just consider it as hc upon e, and this is 2m upon e, right? We need to find lambda 2 upon lambda 1, so let's just divide them. So we will get h upon root 2 me. Yeah, so it will be some constant k, and this will be root e upon e. So it will be k upon root e. So it will be e to the power minus 1 by 2. So D will be the option, right? Let's move on to our third question. So we have a particle of mass m decays into two particles m1 and m2. Okay, so we have a particle, it is at rest, so u is 0 and they will decay. So this is m1, this is m2. Let's say m2 is going like this, v2, and m1 is going like this. So having non-zero velocities, the ratio of de Broglie wavelength. Okay, so this is quite easy, right? So if we conserve momentum, so mu will be equals to m1 v1 minus m2 v2. Okay. So this is 0. So we will get m1 v1 equals to m2 v2. Okay. And if momentum is same, then de Broglie wavelength depends on p. Both have same momentum, so de Broglie will be same. So ratio will be 1:1. Okay. So again, quite easy question. Let's move on to our fourth question. So let's move on to our fourth question. Okay. So this is fourth and this is fifth. Right. So in this question, we have a photon falls on the cathode plate in a vacuum tube. The work function is phi. So energy of photon will be equals to hc upon lambda, and the work function is phi. These two information are given. This distance is d, right? So the distance from the cathode is d. Now, a potential difference V is maintained between the electron with the minimum de Broglie wavelength of the electrons passing through the anode is lambda. So we have to find the de Broglie wavelength of electron. It will be h upon p, which is h upon root 2 mk. This is the kinetic energy. And how we can find the kinetic energy? It will be hc upon lambda, which is energy of photon minus function. So these two equation we have. Okay, so this is first, this is second. Now, which of the following statement is true? Right. So let's start. A option is, for the large potential, V is much larger than phi by E. So look, uh, this is V, right? Now electron will come out here, and in the potential difference V, they will have some kinetic energy, which is EV. Okay. Now look, if I'm giving them some energy, so work function will take some energy out and we're left with kinetic energy. But as you can see, V is much larger than phi by E. So V is much larger than phi by E. So this energy which we get, right? So this energy which we get from the photon after the photon ejects an electron, right? It will be much smaller than this V. Right? So look, so if I write, this will be E V naught will be equals to hc by lambda minus phi. So V naught will be hc by E lambda minus phi by E, right? Now this V naught is what? It is stopping potential. It is stopping potential. This is our stopping potential. And this V is attracting the electron. So as we see, V naught will be much less than V. Okay, V naught will be much less than V. So actually the total energy or the kinetic energy of electron will be E into V itself. Are you getting me? Because if you add them EV plus EV naught, let's add them. So it will be approximately EV, right? This potential is quite large. It's very large. Okay, so the potential difference we are giving, it's quite large. So it will be EV. Okay. So if you put the here, so lambda E will be h upon root 2 MEV. So lambda E is proportional to root V. So if you make it 4 times, lambda will be half. So this is correct. Okay. Now lambda decrease with increase in phi and lambda pH. So let's move on to this. So if you put, okay, now let's say the potential is not given, right? Let's say the potential is not given because these points, they are not mentioning anything about this potential difference which we are applying. Okay. So lambda E decrease with increase in this. So okay, let's consider them. So the kinetic energy will be this. Okay, so let's just put these values now. So lambda E will be h upon root 2me v plus v naught. So it will be v plus v naught, right? So v plus v naught. Now let's put the values. So it will be, so this is all these constants. So this is constant upon root the value of v plus, so v is v, which is the potential we are giving. So it will be plus, and v naught will be hc upon e lambda minus phi by e. Okay, so this will be our de Broglie wavelength. Now it decreases with increasing phi and lambda pH. So if I increase, this is lambda of pH, right? Photon. So if you increase this, the whole value decreases, and this whole value decreases. This means this whole value will decrease, and if this decrease, lambda will increase. So this is correct. Let's increase phi. So if you increase phi, this whole value. Oh, okay, okay, wait. If lambda increases, this whole value decreases. So if this whole value decreases, lambda will increase. So this is wrong, right? With the increase in lambda, the lambda of p will increase. So this is wrong. Lambda increases at the same rate as lambda pH. So it is not, right? So the rate won't be same. So this is again wrong because it is in the root, right? So rate will be same is if they are direct proportional. So if lambda E is directly proportional to lambda P, lambda pH, which is not the case. So it is in the root. So this is wrong again. Okay. Let's move on to D. So lambda is approximately half if D is doubled. This is wrong. Okay. Why? Look, the potential V does not depend on D, it is depend on the battery itself, right? So it will not get affected. So this is wrong. So only A option is correct. Okay. So this was a quite interesting question, I must say. Let's move on to our fifth question. So when the photon of energy this strike a surface metal A, the ejected electron have maximum kinetic energy Ta. So we can write Ta is equals to 4.25 minus phi. Okay, the maximum kinetic energy of photoelectron liberated from another metal B with the photon this is this. So TB, which is Ta minus 1.5, will be equals to 4.70 minus 5B. Okay. Now the de Broglie wavelength of these photons is lambda photoelectrons is this and this. Okay. So for this we can write lambda A will be 1 h upon root 2 mTA, and lambda B will be h upon root 2 mTB, and this is TB actually, right? So if I divide both of them, so lambda A upon lambda B is 1 by 2. So this is actually 1 by 2. So it will be root TB by TA. Let's square them. So we will get, so this TA will be 4 TB. So TA will be 4 TB. If I put the value, so TA is equals to 4. TB is TA minus 1.5, right? So it will be minus 3 TA will be minus 6, right? So TA will be 2. So if TA is 2, then phi A will be 4.25 minus 2, be 2.25, right? So phi A we get, phi B we can also find. So if TA is 2, then TB will be, so if this is 2, so it will be 0.5. Okay, yeah, and you put those values here. So 0.5 minus 4.7. So phi B will come out to be 4.2. So phi A is this correct, phi B is this correct, TA is correct, and D is not correct. Okay, so quite easy again. Let's move on to question number 6. So here we have two questions. This is sixth. This is seventh. Okay. Now, so we have a proton is fired from very far away towards the nucleus. Is this? It makes the closest approach. Okay. So let's say this is proton. Its charge is E, of course. It has a V. Now it will reaches over here. Okay. So what happens is its kinetic energy will be converted into potential energy, which will be K Q1 Q2 by R, right? The de Broglie wavelength we have to find. So let's just find the kinetic energy. So let's say if this is K, kinetic energy KE we can write. So it will be K 9 into 10 is power 9 Q1 is E and Q2 is 120 E divided by R. So it will be 10 into Fermi 10 raised to power minus 50. Okay. So let's just not calculate this. Let's directly find the lambda. So lambda will be h upon root 2mk. So h upon root 2. Mass of proton is 5 by 3 into 10 raised to power minus 27 we have to take, and k is this. So let's put 9 into 10 to the power 9 into e square into 120 divided by 10 into 10 raised to the power minus 15. Okay. So e square will come out and becomes e. So let's just cancel out some more things. So 5, 2, this 10 will get cancelled and this will be 40, right? So we have 9, 4 and e square. So they will come out. So it will be h upon e, 3 and 2. Okay. And we have 10 here and this. So this will be 10 raised to power 10. So this will be 10 raised to power 10. So minus 27 plus 10 and this will be plus 15. Okay. So we will be having minus 2, which will be 10 raised to power minus 1. Now h upon e is how much? H upon E will be 4.2 into 10 raised to power minus 15 divided by E. So H upon E we have put already. This will be 6 into 10 raised to power minus 1. Okay. So simple, it will be 42 by 6 Fermi meter, which is 7 Fermi meter. So 7 will be the answer. Okay. Let's move on to the seventh question. So we have an alpha particle and a proton are accelerated from rest. The potential difference this. Okay. So if we have a proton, the mass of proton, let's say it's m. So mass of alpha particle. So mass of alpha particle will be 4m, right? Okay. Because it has two protons and two neutrons. So it will be 4m. Charge of Qp is Q. So the charge of Q alpha will be 2, 2Q, right? So it will be 2Q. Okay. Now we have to find this. The potential difference is same. So the kinetic energy of this will be Q into V, but the kinetic energy of, so this is proton, kinetic energy of alpha particle will be, it will be 2Q into V. Okay, so let's find the lambda for proton. So lambda for proton will be H upon root 2mPQV. So it will be root 2mQV. Now let's find for alpha. It will be H upon root 2 m alpha will be 4m and k will be 2qv. So if you divide lambda p upon lambda alpha, it will be 1 upon root 2. So this will be 1 upon root 4 for 16. So we will get root 8. So it will be 2 root. So we have to find the nearest integer. So 2 root 2 is what? 2 into 1.4. So it will be 2.8. So this is 3. So 3 will be the answer. Okay. So these are quite easy. The questions on de Broglie are quite easy, right? So let's move on to question number 8. Question number 8. So we have three questions here. right? So this is our eighth, ninth, and 10th, right? Okay, right. So this question is based on Davis and Germer experiment, right? Okay. So we know this concept, right? These are atoms, layer of atoms, and if you project an electron beam like this, okay, like this. So this will be the path difference, right? Let's say this is A, B, C. So delta x will be AB plus AC, and this will come out to be, if look, this is D, right? And this angle is theta, right? The layer of the horizontal layer of atoms with the incident is theta, right? So these will come out to be 2D sine theta, right? And delta x turns out to be, so if we are talking about constructive interference, then this will be like this. And if you want to consider it in I, so it will be 2D sine. So if this is I, then this will be 90 minus I, right? And lambda. So and lambda will turn out to be 2D cos I, right? So we can use either this or this according to question. So if I is given, then we'll not use this, we'll use this, right? Okay, so we need to find the electron accelerated by the potential V. So how much this will be? Okay, so like if we put N1, then lambda will turn out to be 2D cos I by, so 2D cos I. So it will be 2 angstrom. So it will be 10 raised to power minus 10. D is in 1 angstrom into cos I. So cos 30. So we will get root 3 into 10 raised to power minus 10 meter. So this will be the wavelength of the electrons, right? So it will be de Broglie wavelength. And now we have to find the potential. So we know lambda is equals to h upon root 2 m e v. Okay, so we can find v as, if you square them, so v will turn out to be h square upon 2 m e lambda square. So if you put all those values, you will get the answer 50 volt, right? Which was the, of course, this is V naught. So this is the voltage which gives a perfect peak at like in the center, right? So the diffraction shows the highest intensity at the center. So C will be the option. Okay. The strong diffraction peak, so this that is called diffraction peak, is observed when the electron are incident at the angle I from the normal. So this is I. De Broglie wavelength of can be calculated by the relationship. So n lambda equal to 2d cos I. So n lambda equal to 2d cos I. So C will be the optional. Okay, so both will be C. Now for the 10th question. So the electron are made to pass through the narrow slit D comparable to the wavelength de Broglie wavelength, okay, that detected by the skin D. So from the slit. So in this, I think we have to find, right. So we have to check for this diffraction pattern, right? So this is the complete question. So which of the following graph are expected to show number of electrons? So intensity will show number of electrons. Now, due to diffraction, the maximum, the first maxima will look like this, right? And the second will decrease like this. So diffraction. So the graph will be same like we have studied in the diffraction, because this is actually the diffraction experiment, right? But this x will be much greater than d. So this x will be much greater than d. Okay. So this is our x here. So A option is correct. In B, of course, it is wrong. So X will not be equal to D, right? This X will be much greater than D. So this is absolutely wrong. These are wrong. So A will be the option. Okay. Let's move on to our last three questions. Last three questions are these. Okay. So this is our 11th question. We have two statement. Davidson-Germer experiment established the wave nature of electron. Absolutely right. If the electrons have wave nature, they can interfere and show diffraction. Right? So majorly in Davidson-Germer experiment, they shows the diffraction through the bombardment of electron on the atom. So the A is correct. No, no, no. So it will be so A is two. So both are correct, right? So A is correct and two is correct and correct explanation. So B will be the answer, right? Okay. So they have interchanged it. Nice. They're messing with us. No. Okay. Let's move on to our 12th question. So we have a potential energy of the particle is given by this. So lambda 1 and lambda 2 are, so for this potential energy, the de Broglie wavelength of particle is lambda 1 and for this it is lambda 2, right? So we know total energy equals to potential energy plus kinetic energy. Okay, let's for the lambda 1. So for lambda 1, the total energy is 2 E naught. It is given, right? The total energy is always 2 E naught. And the potential energy, so potential energy 1 is E naught. So the kinetic energy will be E naught. Okay. And for the lambda 2 case, the total energy again is 2 E naught. The potential energy is 0. So the kinetic energy will be 2 E naught. Okay. So let's find the lambda 1. So lambda 1 will be h upon root 2 m E naught. And lambda 2 will be h upon root 2 m 2 E naught. So lambda 1 upon lambda 2 will be 1 up, h upon root 2 m E naught upon h upon root 2 m 2 E naught. So it will be root 2 times. Yes, this will go. So it will be root 2 times. Okay, it's quite easy question again. Let's move on to our last question, the 13th one. Assume d Broglie waves are associated with an electron can form a standing wave between two atoms arranged in one-dimensional array. So we have some atoms like this. Okay, and with the nodes at each atom. So these are the atoms, right? And these like behave like nodes. So these we have nodes. Okay, so it is confirmed that on the atom there will be a node. Now distance between the atoms is 2. So if this is D, so D is given 2 angstrom, right? We get a standing wave. Now the similar standing wave again formed if D is increased to 2.5 angstrom. So this is, let's say, D1. Now if the D2 is 2.5 angstrom, then again we can get the standing waves, but not for any intermediate value. So between them, there is no value of D for which we get standing wave. Okay, so let's make the situation. Let's say this is atom 1, this is atom 2. So I'm making atom 1 and atom 2. Now at these and these nodes will there. So situation can be like this, okay, or it can be like this. Yeah, are you getting me? Or it can be like this. So as these can be all those possible combinations, right? Right? So there is no node between them. So between them there is only one node. So there is so like this. Okay. So let's say when the distance was a d1, right? When the distance was a d1, so there is n nodes. So if distance between atoms was d1, then in between atoms there are, let's say, n nodes. Okay, so n nodes. Now look, if there are two nodes, then this is 3 lambda by 2, right? So if there are n nodes, there are n nodes. So if there are two nodes, this is 3 lambda by 2. So there are n nodes, then it will be n plus 1 lambda by 2 will be equals to d1. And if you increased by 0.5, then only one more node will come in between, right? So we can say, so when it is at d2, then it will be n plus 2 lambda by 2, right? So one more half loop will come. Okay, so if you subtract them, we'll get minus lambda by 2 will be equals to d1 minus d2, right? And d1 was 2 minus 2.5. This will be minus lambda by 2. So we will get lambda by 2 is 0.5. Lambda by 2 is 0.5. And this is the, like, we have studied the organ pipes, right? Okay, and the closed, like a string bounded from both ends, right? So this was the fundamental. So this was the fundamental frequency, right? This was the fundamental. Okay. So, and this makes lambda by 2. So lambda by 2 minimum is 0.5. Okay. So find the energy of electron in electron volts and the least value of T for which standing wave of this type can be described. So the least value is lambda by 2, which is this 0.5, right? Which is equals to our D, which is D minimum to be precise, right? Which is 0.5. Now, for any cases, lambda will turn out to be 0.5 into 2, so it will be 1 angstrom. So lambda is 1 angstrom, right? So energy of electron will be hc by lambda, right? So it will be hc by lambda, right? Now, if you put those values here, so what will get? So it will be H is 12400 upon 1 angstrom. So it will be in electron volts, right? So we will get 12400 electron volts. Yes, I think this is the answer. Mm, so the wavelength we get is 1, right? So this is the energy of photon. What do we have to find? Energy of electrons. Okay, so we have to use the de Broglie expression, not this. It's electron, right? So it's electron. If it is electron, then lambda will be h upon root 2m k. Okay, so lambda is this. So we'll find k will be, if you square them, so it will be h square by 2m lambda square, right? So it will be 6.6 into 10 raised to power minus 34 square. Like the before we have done this question, the mass of electron will be 9.1 into 10 raised to power minus 34 minus 31, right? So this is 34, this is 31 into lambda square till 10 raised to power minus 10 to the whole square. So kinetic energy will turn out to be, if you solve this, 2.4 into 10 raised to power minus 17. 2.4 into 10 raised to power minus 17 joule. Okay. So we can find also it in EV. So in EV it will be, so kinetic energy in EV, it will be 2.4 into 10 raised to the power minus 17 divided by 1.6 into 10 raised to the power minus 19, right? So this will be in EV. It will come out to be 151 E. Okay, and the D minimum we have already calculated, it is 0.5. So right, quite easy question again. I've just considered, like, it says the energy of electron, and I have by mistakenly used the formula for the photon. Okay, so be careful. These mistakes can happen. Okay, so let's just finish today's videos. today's video. Thank you.